The chemistry of water. What makes it so special? At first glance, water appears unassuming. Just two hydrogens and one oxygen. Yet at the molecular level, it behaves like a quantum anomaly, a fluid matrix whose structural and reactive nuances govern everything from biological homeostasis to nanotechnological purification systems. The H2O molecule is bent, not linear, forming an angle of approximately 104.5 degrees. This geometry, combined with oxygen's significant electronegativity, approximately 3.5 on the Pauling scale, creates a polar molecule with a permanent dipole moment. In other words, water has a partially negative region near the oxygen and a partially positive region near the hydrogens. This polar nature makes it an exceptional solvent and explains its capacity to form hydrogen bonds. Hydrogen bonding arises from the electrostatic attraction between the partially positive hydrogen atom of one molecule and the lone pair on an electronegative atom, in this case, oxygen. Each water molecule can engage in up to 4 hydrogen bonds, forming a dynamic, fluctuating lattice. These transient interactions endow water with emergent properties: cohesive behavior, capillarity, and a high specific heat capacity. One of the most fascinating aspects of water is its ability to ionize itself, a process called autoionization. Here's the equation below. This equilibrium, governed by the ion product constant of water, Kw equals 1 times 10 to the power of negative 14 at 25 degrees Celsius, forms the basis of the pH scale. Since free protons, H+, don't exist independently in aqueous environments, we reference the hydronium ion, H3O+. The pH, defined as negative log times the concentration of hydronium, quantifies the proton activity in solution, meaning each unit represents a tenfold difference in hydrogen ion concentration. A solution with pH 6 is 10 times more acidic than pH 7, and pH 5 is 100 times more acidic. Likewise, each step in the scale reflects increasingly dominant hydroxide ion concentrations, with basic solutions above pH 7 having excess hydroxide ions relative to hydronium. This delicate balance of ions gives rise to acid-base chemistry and regulates countless biological and environmental systems. In water treatment systems, especially those utilizing nanobubbles, pH is not just a number, it's a control lever. At higher, basic, pH, hydroxide ions, OH-, accumulate at the bubble interface, conferring a negative zeta potential. This electrostatic repulsion between like-charged surfaces stabilizes the bubbles in suspension, preventing coalescence. Consequently, pH modulation becomes a tool for engineering both bubble stability and contaminant solubility. Water is not just a solvent, it's a dynamic, polar, and self-reactive medium. Whether you're designing nanobubble systems, distillation columns, or electrochemical treatments, one truth remains: every effective purification strategy must account for water's polarity, its hydrogen bonding network, and the delicate equilibrium of pH and ion concentration. Master these variables and you'll master the chemistry of purification. Thank you! If you enjoyed this video and want to learn more, like and subscribe. Up next, we explore water's phase changes. See you there.